All right, so we started algebraic derivatives yesterday with the power rule, right, and E. We're going to look at graphical derivatives today. Okay. So just as a reminder, does this word sound familiar? Differentiable. I don't know if I've mentioned it. Okay. This means a function has a derivative. Okay. Where did I mention that that derivatives do not exist? So we're not differentiable at corner, right? Line bird. And discontinuities, yeah. Finish my letters off there. What function? I'll let you write that down. What function produces corners? Piecewise could. Most commonly, which is in fact a piecewise function. It's just a special one that we highlight. Okay. What most commonly produces our discontinuities? A piecewise function. Right? And rational functions. Those are the fractions, right? Those are our most common discontinuities that we study. Does anybody know what produces a cusp? It could.
It's whenever it has an asymptote.
There's no asymptote here. That's good. Good try.
They touch?
Yep, those come together in a point.
So it's like it looks like very infinite.
Like a sine wave?
It's
Is that final?
Rational?
a rational exponent. Okay. I think the even's on the bottom. Let's check. Because one way or the other, they're different. So if you have a calculator, put that in.
Yeah, it just goes off to the
Okay, so actually it's the opposite of what I'm thinking then. So that's x to the 5/4. Okay, what if I put in x to the 4/5? There's the line bird. You can kind of see the curve there. Right, so this will form a cusp, so it doesn't need to be switched. It's
on the bottom.
Yeah. Those are the most common cusp producing equations. Okay. If you think about it, it's x to the 4th, the 5th root, right? This is always going to produce evens. because it's the fourth power. So the graph will always stay in the evens, even y values. So go ahead and zoom in on that. See how it becomes more obvious as you zoom in? Okay, you could just keep, this is one way to check differentiability just in an informal manner. Okay. Is just keep zooming in. And you can see that as we zoom in, does that ever produce a nice curve? No, it just keeps getting more and more pointy, right? So this is one way to kind of informally check for a corner or a cusp. If I checked absolute value of x, I get the same situation, right? Yeah. Okay. What if I did, let's just do x cubed minus x, whoops, still not used to that feature, minus x squared plus x. Well, that's just, I made that up, so hopefully it works. Standard. Okay, that'll work. So we have a cubic, right? What if I zoom in? Still see the curve, nice smooth curve, right? Just keep zooming in. Curve. Is it curved? So it's got a little curve to it, right? But you see how it's not got a point or anything in it, right? Does that look straight? Okay, so we zoomed in 4 times, and it looks like we've got a straight line. Yeah. This is called local linearity. Okay. You can estimate the slope of that line using your calculator. Okay. And again, it's very informal. So to estimate the slope of this line, how would I grab 2 points off of that?
Trace.
Yeah, you trace it. Okay, take your pick, I don't, right? There's an x and a y. There's an x and a y, calculate the slope. Very informal way to calculate, estimate a tangent line slope.
The equation broke up.
Okay. So that's called local linearity. Any questions there? Just a handy tool just to visualize graphs and derivatives. Okay. So are we good there on what is not differentiable and what may be? Okay. So we know we need to point this out. If f of x is not continuous, f is not differentiable, right? We already determined that. What if f is continuous? Do we have to have differentiability?
Not only.
Is that continuous?
Yeah.
Is it differentiable? Okay, so keep that in mind. If f of x is continuous, f may be differentiable. Okay. Okay, here's something neat in math, it's called the contrapositive. I'm not going to require you to remember this, but it can come in handy. The contrapositive of this is we flip the two if-then statements and negate them. So we would say if f is differentiable, right? Then f is continuous. Is that true? Yeah, it is. The contrapositive is always true. If the original is true. So that's handy. But this is a key piece of information because sometimes on a free response you'll say, it'll state f is differentiable. And it'll go into some theorem like the intermediate value theorem, which requires continuity. You have to make that connection. Okay. You actually have to state because f is differentiable, f is continuous. That key idea there. Okay. All right. Good. Just a little extension from yesterday at the end. All right. Graphical. How many of you are good at visualizing area and volume and graphs and stuff? You can just like see stuff and manipulate with your mind, shapes. Some of you? I know that's how I was.
Is that necessary?
Not necessary, but it helps. Some of you are algebraists. You're better with symbols. Okay. Let me give you better than you think. We'll give you some graph. It's a quadratic, right?
Yes.
Okay. Can you draw a sketch of the derivative?
So you just draw a tangent line, right?
It doesn't say graph or sketch the tangent line at some value.
So then you just...
Okay, so f of x has x and y values. We can do the same thing for the derivative. Okay, so what is the derivative value right here?
Zero.
Right, it's a horizontal tangent line, right? So the f prime of x here is 0, right? So I'm going to put an actual 0 right there. Evelyn? There's, okay, so what is this slope right here? Positive or negative?
Oh,
Negative, and then over here it's, do we have to pass 0? Yeah, we do. Negative to positive, we pass 0. So there is some point here where the horizontal line, the tangent line has to have a slope of 0. Does that make sense? Okay. We just established that the derivative over here is negative, right? And the derivative here is positive, right? Right. It's just slope, right? Negative slope, positive slope. Does it get steeper as we go this way? The negative number gets bigger, right? Steeper and steeper. Okay. So this would be a larger negative. Would this positive get bigger here, steeper? Yeah, so larger positive. Okay, good. Okay, so get the idea of slope, right? Just looking at that graph. If we have a slope of 0 here, and my slopes are negative, so the value of the slope is negative, right? Down here. Are they getting bigger? The values are getting more and more negative, right? And the values on this side are getting larger positives, right? So if you graph the derivative, the graph of the derivative, a sketch of it will look like that. Yeah, I always base it off where the derivative is 0. Because that we know is an accurate spot, right? And then we just say positives or negatives.
So then if this was a negative x squared, would it just be reversed?
It would be different, yeah, just the opposite.
So why did you make your slope be positive?
Here?
Yeah.
Because the slope is positive.
Not the red line. Why did you make that positive?
Because the further left you go, the larger the negative number for slope, right? So that you go left, you have some, let's say it's -2. Go farther out, the slope is steeper, let's say it's -10, right? So it's going to be down here more.
Why couldn't you invert it, like flip it?
This way?
Yeah.
That would be this quadratic.
Okay. Let's see.
Like that. Okay, slope is 0 here, right? So I'm going to put 0. Okay, the slope is positive or negative? Negative. Slope is positive. That's what would invert that line. It's just determined on where your zeros are, whether slope's positive or negative.
So you essentially you make a straight line for a curved line? To
The derivative, okay, the function here is a negative x squared.
Okay.
What's the derivative using the power rule?
Negative 2x.
It's a linear function, right?
Yeah.
So the derivative's a quadratic, or the function's a quadratic, the derivative's a linear. So that's all we're doing is graphing this linear function. Estimating it, we're sketching it. Okay, you can do it with the function, exactly, but most of the time, we're just going to say, here's a graph. What's the derivative graph look like? Okay. It's just an exercise in identifying visual horizontal tangent lines and positive and negative slope.
So the derivative line is just a linear line to represent the curved line's slope.
Right. These values, like if I said, okay, what's this point? Let's call it 4, -2. Right? That means f prime at 4 is -2. Okay, what does that tell me about the original function?
-2 squared is 4.
At 4, the slope of a tangent line is -2. Right? That's what that's saying. -2. Right. Okay, so you have just mapped all the possible slopes of this function. That's all you're doing. Yeah, it's kind of confusing, isn't it? You guys are looking at me like you just got hit by a truck.
Looking at you like the screen's not there.
I like to show that. That's all.
Flash it every once in a while.
Actually, this is really pretty.
Good times.
Right, you guys lost before that.
All right, let me see if this will help.
I didn't think
What if I give you
$1 million.
If I had $1 million.
I'm honest.
Okay, let's call that f of x. What does the derivative graph look like?
Pyramid.
So you've identified this, what kind of a function is it?
Cubic.
It's a cubic, so the derivative will be a
Cube.
quadratic, right?
Yeah.
Because if you have x cubed, the derivative is 3x squared. So we know it's going to be a u of some kind, right? Again, start with your horizontal tangent lines. Where does that occur?
There.
Here? Here?
There.
So there is a horizontal tangent line here, right? So the value of the derivative is 0. The slope is 0. Where else?
The other parallel.
Yeah. Horizontal tangent line, slope is 0. In here, slope is negative, right? Okay, here, positive, and here, positive. If I know this kind of looks like a quadratic, right, I need positive values, negative values, and I need positive values. That's our derivative graph. Okay. Okay, so yeah, think about this. I don't do that on purpose, I swear.
Sure?
Let's call that x equals 2.
Okay.
F prime of 2 is 0. F at 2, okay, sure. Right? So at this point, 2, -4, the slope of the derivative is, or the slope of the function is 0. Slope of the tangent line. So it's just a visual way to look at derivatives versus functions. Okay. Yeah, I know it's hard the first time around. Evelyn. Why did I draw a parabola? These points have to be connected.
So we use a function that has, like, so x-axis twice, so
That's a quadratic, yeah.
oh, sorry.
Yeah, so these, everything's continuous when we do derivatives, right?
Okay.
These points always have to be connected then. The only way, if it's all negative numbers, the only way to connect them is just to bring them together in a smiley or a frowny face. But this would be positive, right?
Right.
So there you go. And think here, you know, the slope is not very steep, but it's getting really steep as we go this way. So the numbers are getting bigger. So the numbers are getting bigger.
I don't understand the U part of it, like underneath the in the quadrat or the quadrants 3 and 4. I don't understand that part of the graph. Where it's negative.
How do you get this?
Yeah, like I get the where it's exponential on the left is right, how it's going up with positive numbers, but I don't think that negative.
Okay. Negative slope? Is this steep or negative?
Yeah.
Right? So it's going to be a smaller number, which makes it go down further. But as we come across that spot, is it coming back up?
Yeah.
The negatives aren't as big anymore, so it's going to come back up to the x-axis to 0. That's another way to look at it. Yeah. Okay.
So if you had something that goes through another time, so how many of these can you have?
If you're asked to analyze something like this, it's going to be a pretty basic.
But what if it did another, it went up and then came down?
You just have another 0 and the graph of the derivative would come back down.
Would be a quadratic.
Right.
And then you said for sine that
Let me
it's
just
not the same thing.
throw something on the board. made it up, right? It's gonna have the same as, probably the same as that one. Where are zeros? Okay, this is negative, right? So we're still gonna have this positive. Yeah, that was a bad example. Slope's positive, so. There's some better ones in the book. Any questions? Try to work through the ones in the book that I give you. And we will continue to work on this, because I know it's kind of hard at first. I had trouble with it too when I was your age. Even though I was a visual person, I still had trouble with it. So. Tuesday we'll get back to the algebraic derivatives. Yeah, I know there's a lot of writing here, but I pick and choose for a reason, you know that. All right. It seems like a lot, but again, it's just a lot of writing.
They'll have to go in the trash.